Hey guys, welcome back to Joanne's Learning Hub. So, this is the study of the composition of an atom, its interactions with other particles, how some atoms spontaneously decay, and the safety precautions we need to take while this happens, along with the core reactions that occur in atomic bombs and in the sun. So, what are we talking about? It is atomic physics. So, let's get started. Let's begin with the fundamentals of the atomic model. Now, this atomic model consists of the protons, the neutrons, and the electrons. The nucleus of an atom contains the protons and the neutrons. The nucleus is very tiny, but it makes up most of the mass of an atom. So, these protons, they are positively charged, so their relative charge is shown by +1. Neutrons are neutral, which means their relative charge is 0. The rest of the atom is mostly empty space, and electrons, which are negatively charged, so their relative charge is -1, they orbit the nucleus at set distances. Now you can also see the actual charge over here, which is measured in coulombs, but the relative charge does not have any unit. There is equal number of protons and electrons in an atom. And protons and electrons, they have equal but opposite charges so that they cancel out and the overall atom is neutral. What gives us the evidence to prove that the nuclear model of an atom is correct? It is the alpha scattering experiment. So let us understand the experiment first. So a beam of alpha particles is fired at a thin sheet of metal foil, which is particularly the gold foil, which is why this experiment is even called the gold foil experiment. So what did we observe? One, we observed that most of the alpha particles pass straight through the sheet and they are undeflected. And second, we observed that very few alpha particles are scattered by the sheet and some are deflected back the way they came. So what do these observations imply? It implies that when most of the alpha particles are undeflected, this suggests that most of the atom is empty space. And since very few particles, the alpha particles, are scattered by the sheet and some deflected along the path they came, it suggests that the atom has a bit of positive charge which is concentrated in the nucleus. And since alpha particles are also positive, they are deflected because they were repelled by another positive charge. Now an additional point is that most of the mass is in the nucleus, since the alpha particles, which had relatively high mass and momentum, were deflected by a stationary nucleus. Now for some definitions. An element is a substance whose atoms all have the same number of protons, but they can have different number of neutrons. So what is a proton number? The proton number, also known as the atomic number, is the total number of protons in an atom's nucleus. The mass number or the nucleon number is the number of protons plus the number of neutrons in the nucleus of an atom. Now, a nuclide is an atom with a particular number of protons and neutrons. So, there is a certain nuclide notation. We can see the X, which is basically shown by the element symbol. The A represents the mass number or the atomic mass or the nucleon number, and Z represents the atomic number or the proton number of the element. Next, we can see two terms, relative mass and relative charge, and you must know the difference between the two. The relative mass of a nucleus depends on the number of protons and the number of neutrons in an atom's nucleus, which is why the relative mass is equal to the nucleon number of an atom. However, the relative charge of a nucleus only depends on the number of protons, because the neutrons are neutral. So, the relative charge is equal to the proton number. Now, isotopes of an element are atoms with the same proton number but different nucleon number due to different number of neutrons. An additional point is that unstable isotopes are isotopes that decay into other elements and give out ionizing radiation as they try to become more stable. So these isotopes are known as radioactive isotopes. So when unstable isotopes give out ionizing radiation, this ionizing radiation has the ability to remove electrons from the atoms it hits, and it turns them into ions. So what are ions? Ions are atoms or molecules that have gained or lost electrons, giving them an overall charge. So if an element has lost electrons, it becomes a positive ion. If it has gained electrons, it becomes a negative ion. In the previous slide, we learnt about unstable isotopes giving out ionizing radiation as they try to become more stable. They do this by the process of radioactive decay. Radioactive decay is the process in which unstable nuclei change to become more stable by emitting ionizing radiation. Now, there are three main forms of ionizing radiation that you need to know: alpha, beta, and gamma radiation. These are also called radioactive emissions. Now, an alpha particle consists of 2 neutrons and 2 protons. So, it is similar to a helium nucleus. It has relative charge of +2 and it has a large mass compared to beta particles and gamma rays. Now, you may be wondering what is penetrating power and the ionizing power. The penetrating power is how much the emission can travel into a material before it gets absorbed. And the ionizing power is how likely the emission is going to knock out electrons from the atoms it collides with. Now, alpha particles have poor penetrating power, but they have very strong ionizing power. This is because alpha particles have more energy in their kinetic energy store, and they also have more charge because their charge is the highest among all the three of alpha, beta and gamma. It is +2. Moving on to beta particles. A beta particle is a fast moving electron. It has relative charge of -1 and it does not have any mass. Beta particles have moderate penetrating power and moderate ionizing power as well. Gamma rays are part of the electromagnetic spectrum and they are also called waves of electromagnetic radiation. They have relative charge 0 and again virtually no mass. Gamma rays have penetrating power which is very strong, but they have very weak ionizing power. This is because gamma rays have no mass and no charge, so they can pass through atoms very easily rather than collide with them. So how are all the three radioactive emissions, alpha, beta and gamma, absorbed? Alpha particles can be absorbed by a sheet of paper. Beta particles can be absorbed by thin aluminium, which should be around 5 mm thick, and gamma rays can only be absorbed by thick lead or meters of concrete. You must remember that alpha can also be stopped or absorbed by aluminium and lead, and beta can also be absorbed by lead. So basically, lead absorbs all the alpha, beta and gamma radiation. Now, we know that in the process of radioactive decay, either alpha, beta or gamma radiation is emitted for the nucleus to become more stable. So, we must understand how radioactive decay affects the composition of a nucleus. When a nucleus emits alpha particle or beta particle, it changes from one element to another because the number of protons in the nucleus is changing. But when gamma decay occurs, there is no change in the number of protons in the nucleus, which is why there is no change in the element. Radioactive decay equations are written in the form atom before decay, then the arrow, then atoms after decay plus the emissions, which can be alpha, beta or gamma emission. Now you must remember that the proton and nucleon number must be equal on both sides of the arrow. Now moving on to alpha decay. Alpha decay occurs when an alpha particle is emitted. We learnt that the alpha particle has 2 protons and 2 neutrons, which means that its proton number is 2 and its nucleon number is 4. So when a nucleus emits an alpha particle, its proton number decreases by 2 and its nucleon number decreases by 4. So an alpha particle is denoted by the symbol A, then 4 on top and 2 at the bottom, and this is its nuclide notation. Now an example of the alpha decay equation. So this is the alpha decay of uranium-238. It decays to thorium-234 by giving out or emitting an alpha particle. Next up is beta decay. So when a nucleus emits a beta particle, a neutron in the atom's nucleus changes into a proton, which means that its proton number has increased by 1. But since the nucleus has lost a neutron but gained a proton, the nucleon number doesn't change. So you must remember that in beta decay, the number of protons increases by 1, which creates a whole new element, but the nucleon number remains the same. So now we can see an example of a beta decay equation. This is the beta decay of C14. It has a proton number of 6, but after beta decay, its proton number increases by 1 to form a new element, which is nitrogen, and it gives out a beta particle. You can see that the beta particle is denoted by the symbol B, beta, and then 0 on top and then -1 at the bottom. So this is its nuclide notation. In gamma decay, there is no change to the proton number or the nucleon number, so the element stays exactly the same, and it gives out a gamma ray, which is denoted by the symbol gamma and then 0 on top and 0 at the bottom, which is its nuclide notation. It's 0 because it is not changing the proton nor the nucleon number. Now we understood that this radioactive decay, it makes the nucleus more stable. During alpha decay, the nucleus becomes less heavy overall. In beta decay, there is a reduction in excess number of neutrons, and in gamma decay, the gamma ray just carries away the excess energy which is present in the atom or element. So how do we detect radioactive emissions? We use a Geiger-Müller detector and counter to detect and count radioactive emissions. So what exactly is this counter? It is a tube which is filled with gas which is ionized when these radioactive emissions enter it. So this causes there to be a small electric pulse which is counted electronically. Now you must remember that a charged particle in an electric field experiences a force. Alpha particles are positively charged, beta particles are negatively charged, which is why both alpha and beta particles experience a force in an electric field and they are deflected. But you must also remember that alpha and beta particles will only be deflected in an electric field if they are not traveling parallel to the field. Since gamma rays are anyways uncharged, they will not be deflected in electric field nor magnetic field. So the first photo we can see here is an electric field which is set up by two flat oppositely charged plates. The alpha particles move towards the negative plate, whereas the beta source moves towards the positive plate. The gamma source is undeflected. Now, alpha particles, you may notice, are deflected lesser than the beta particles. Why? Because alpha particles have more mass than beta particles, so they are deflected lesser. Now, alpha and beta particles are also deflected in magnetic fields. Since these are charged and since they are moving, they resemble an electric current. Alpha particle moves in the same direction as conventional current, whereas beta particles move opposite to the direction of conventional current. So, we can use Fleming's left-hand rule to find the direction of an alpha particle's deflection. So, you should try this left-hand rule on your left hand too, as shown in the diagram, to help you remember this rule better. So, the thumb represents the force, your first finger represents the direction of the magnetic field, and your second finger represents the direction of the current. You must make sure that all these three fingers are at 90 degrees to each other. So if we see the second photo over here, the magnetic field is going into the page, which is why it is shown by a cross. So your first finger, which is shown by magnetic field, points into the page. And since the alpha source is the same as the conventional current, your second finger will also point 90 degrees and the force acts upwards, which is why your alpha source in this case is experiencing a deflection towards the top of the page. The beta source will move opposite to this, since it is opposite to the direction of conventional current. And gamma rays, they are uncharged, so they will not be deflected. This slide is about nuclear fission and nuclear fusion. Nuclear fission is a type of nuclear reaction where a heavy unstable nucleus, for example uranium or plutonium, splits into two smaller nuclei and releases energy. In nuclear fission, the nucleus has to first absorb a neutron before it splits. So what is the result of this heavy atom splitting? It forms two lighter elements that are roughly the same size. It releases gamma rays and 2 to 3 neutrons also. The total mass after fission reaction is lower than the total mass before fission reaction, since some of this mass is converted into energy. And this energy is transferred to the kinetic energy stores of products, or some of it is carried away by the gamma rays. The energy which is released in this nuclear fission reaction has many uses. For example, it can be used to heat water and even make steam to turn turbines and generators and produce electricity. Nuclear fusion, on the other hand, is a reaction in which light nuclei join together. That is, they fuse to create a larger, heavier nucleus, and this releases lots of energy. So, the two light nuclei in this case, they have to collide at a very high speed to fuse. And what is the result of this fusion? A heavier nucleus forms and lots of energy is released. You must remember that in nuclear fusion releases more energy than even fission for a given mass of fuel. The total mass of these two lighter nuclei is higher than the mass of the new heavier nucleus that has formed, as some of the mass is converted to energy, and this energy is taken away by gamma rays usually. In the previous slides, we learnt about the process of radioactive decay. So you must remember that this is an entirely random and spontaneous process. Next up is half-life. Now, half-life is the time taken for the number of nuclei of a radioactive isotope in a sample to halve. Half-life has another definition as well. It can also be said as the time taken for the count rate of a radioactive substance to halve. So, when the number of nuclei of a certain radioactive isotope has halved, the mass of that isotope has halved as well. Now here is a sample question. A sample of radioactive material is placed near a radiation detector. A count rate of 4,800 counts per second is detected from the sample. After 36 hours, the count rate has fallen to 600 counts per second. So calculate how many more hours must pass for the count rate to become 150 counts per second. So first, we will find the number of half-lives this radioactive sample has gone through to reach 600 counts per second. To do this, we keep on dividing this number of 4,800 until we reach 600. So we first divide 4,800 divided by 2, so we get 2,400. Then again divide by 2, we get 1,200. And we divide by 2 again, we get 600 counts per second. So we can see it has undergone division 3 times, which means it has gone through 3 half-lives to reach 600 counts per second. So next we divide the number of hours, 36 hours divided by the number of half-lives, which in this case is 3. So that is 12 hours. So we now know that one half-life is 12 hours. Now we need to reach from 600 counts per second to 150 counts per second. So 600 divided by 2, which is 300, and 300 divided by 2, which is 150. So 2 divisions, which means that 2 more half-lives it has gone through, which is 12 plus 12, which is 24 more hours for the count rate to become 150 counts per second. Now this is another half-life question which involves graphs. In a laboratory at a nuclear power station, a radiation detector is connected to a computer. The readings recorded are displayed on the computer screen. The detector is switched on. 10 minutes later, at time t is equal to 10 minutes, a small sample of radioactive material is removed from a nuclear reactor and placed near to the detector. Readings are recorded for a further 40 minutes. Figure 11.1 shows the display. So we have the graph, it shows count rates in counts per minute and time t per minute. Now A. Use figure 11.1 to determine the background count rate in the laboratory. So now background count rate, or in other words the background radiation. So what exactly is this background radiation? It is low level radiation that is around us all the time and it is not particularly harmful. So sources of this background radiation includes in the air, in food and drink, in building materials, rocks under our feet, and even from space, which comes as cosmic rays. So in this case, we must read off the count rate where the graph has leveled off. And here, if we see very carefully, it is at 12 counts per minute. So the background count rate is 12 counts per minute. B. Use figure 11.1 to determine the count rate due to the radioactive sample at t is equal to 10 minutes. So we need to determine the count rate as at t is equal to 10 minutes. So on our x-axis we can see 10 minutes. Find the corresponding value. So we have the count rate as 84 counts per minute, but it is not corrected for background radiation. So in this case you are required to subtract the background count rate which we had calculated in the previous question. So 84 minus 12, which will give us 72 counts per minute, and that is the answer of B part 1. Now part 2. At time t is equal to 19 minutes. Again we find the corresponding value, so we'll take it as 21. So 21 on this graph, corrected for background radiation, so 21 minus 12, so we will get 9 counts per minute, and that is the answer of B part 2. Now we'll be learning about the uses of radioactive emissions, alpha, beta and gamma emissions. By using all the properties we have learned throughout the slides, including the half-life, which will have an important role in each of these uses. Now, alpha emitters are used in smoke detectors. So how do these smoke detectors work? Alpha particles ionize the air particles that is there in the smoke detector, and this causes a current to flow. So if smoke is there, it will enter the detector and the smoke attaches to the ionized air particles and makes them uncharged, because alpha particles will make it charged. So when the smoke attaches themselves to the air particles, it will make them uncharged, and this will cause the current to fall, and thus the alarm goes off. Why is alpha particles used? Alpha particles are used because they ionize air particles much more easily than beta and gamma emissions. In terms of half-life, in this use, alpha emitters must have a very long half-life to avoid needing to replace it in the lifetime of the detector. Moving on to beta emitters. Beta emitters are used in thickness gauges. Basically, they are used to help control the thickness of things like paper. So the process goes like this. The radiation is directed through the paper, and a detector on the other side detects the level of radiation that passes through the paper. So if this level of radiation changes, the control unit adjusts the roller to give the correct thickness again. So why is beta particles used? Because beta particles are only partly blocked by paper, so it is best for this use. And again, the beta emitter must have a long half-life. Moving on to gamma rays, which have quite a lot of uses. Their first use is to diagnose and treat cancer. Now, in the process of diagnosing cancer, a medical tracer of gamma source is put into a body. So what is this medical tracer? It is a radioactive substance that is put into a patient's body, and the path of the substance is tracked by a detector outside the body. So this can be used to diagnose cancer. And why is the gamma source used? Because the gamma rays can pass out of the body very easily, so it can be detected. In this use, it is weakly ionizing, and it must have short half-life. Now, gamma rays are also used in treating cancer through the process of radiotherapy, where a high dose of gamma rays is directed to the cells of the tumor to kill them, but the dose to the rest of the body is kept low. Now, gamma rays can also be used to sterilize food and equipment, and for this use, the gamma rays must have a long half-life. Ionizing radiation can be harmful even to living things and living cells. They can ionize living cells and cause tissue damage. So we must find ways to handle and store it safely. Now, this radiation, ionizing radiation, can enter living cells and ionize the atoms and molecules. So the forms of tissue damage is basically burns on human skins, or it can be even worse based on the intensity of the dose of radiation. So lower doses will cause minor damage without killing cells, but if there is long-term exposure to the same lower dose, it can cause the creation of mutant cells which will divide uncontrollably and cause cancer. Now, higher doses can be fatal because they kill cells completely, and it can even cause radiation sickness. So, now what are these precautions that we must take while handling as well as storing radioactive sources? You must wear gloves, you must minimize your exposure time, you must keep maximum distance from the radioactive material. So you must try to use things like tongs, and you must store all your radioactive substances in a lead-lined box. because we have learnt already that lead can absorb all kinds of ionizing radiation. So this was a complete study of the atomic physics as per the IGCSE syllabus. I do hope you found this video helpful. Please do remember to like, share and subscribe to my channel for more videos like this. Thank you.